Okay, so today we're going to be solving systems of equations using substitution. When I think of substitution, I think of a football field or a basketball court or a volleyball court. When your substitute comes in for you, it replaces you. You both don't stay on the court or in the field. One comes out and then the other one goes in. So think of that when we are doing this. So again, we are trying to determine the we are trying to determine the solution. So do they intersect at one point? And if so, what is that one point? Or are these parallel and end up being no solution? Or are these coinciding lines, so in other words, on top of each other, so there's infinitely many solutions? So when we are using substitution, what we are looking for, and these are okay to actually be in any form. So I'm looking at this one, and I'm looking at the coefficients. I have a 1, a positive 3, a 2, and a negative 3. So if I'm using substitution, you are going to be looking for the ones that have a coefficient of either 1 or negative 1. So this is the only one that has a coefficient of 1. So this is the variable I'm going to solve for. And I would solve for x. Remember the literal equations that we did at the beginning of chapter 2, I believe. We are going to subtract 3y on both sides, which leaves me x equals, if you want to write the variable first, it doesn't matter. I'm just going to leave it as is and do 2 minus 3y. So what that means is that anytime I see an x, I can replace it with 2 minus 3y because x equals all of that. Now, it's very important that when you substitute it in for the x in the other equation. Because if you put it in here, you're going to end up with what's called an identity. And we don't want that. So we're going to substitute that. 2 comes down, so 2 times x. So it's 2 times my 2 minus 3y. Subtract 3y and equals 22. So all I have done so far is I have replaced or substituted my x with that. So I now have, when I distribute, 4 minus 6y minus 3y equals 22. We're right back to solving an equation. So 4, combine these like terms, minus 9y equals 22. And subtract 4 from both sides, which gives me, don't forget that, negative 9y equals a positive 18. Divide both sides by my negative 9 to get the y by itself. And I have y equals negative 2. Now, we are half done with that problem. Remember, if we are solving systems, we are looking for, let's go back to what we did in graphing. We are looking for the one point where they intersect. So we are looking for an entire ordered pair. And we're looking for an x and a y. So right now we only have the y. So I now am going to substitute a second time. And I can put this value into either one of those. I'm going to look and see which one looks the easiest. I'm going to choose this first one because the numbers are smaller. There's no negatives in there. As opposed to this one, I have a negative here. I have a 22, which is fairly large. So I'm going to take this and substitute it in for this y. So I'm just going to copy this down so you know what I'm doing. Oopsie, it's a 2, not a 22. And y equals negative 2. So I'm going to take this negative 2 and substitute it in for that y. So x plus 3 times a negative 2 equals 2. X minus 6 equals 2. Add 6 to both sides. And I have x equal to 8. So my final answer is the ordered pair of 8 and negative 2. So if I were to do this by graphing, these two lines would have intersected at that ordered pair of 8 and negative 2. Now I think this is correct, but one of the great things about solving systems is that they're easy to check. But remember, this ordered pair has to work in both of them. So I'm going to show my check over here. So I have I'm going to bring this down. Here we go. So my original is x plus 3y equals 2. I'm going to put my 8 in for x, and my negative 2 in for y. So 8 plus 3 times a negative 2 equals 2. 8 minus 6 equals 2, and I get 2 equals 2. Okay, so it works in that one. I'm going to now check it in my other one. I know it's off the screen, but trust me, the second problem is 2x minus 3y equals 22. And I'm going to, again, take the 8 and put it in for x, and the y, and plug the negative 2 in. So 2 times 8 minus 3 times my y of negative 2. There's 16. Negative 3 times a negative 2 is a positive 6. And I end up with 22 equal to 22. So it also checks in that one. So I know that my answer to this system is 8 and negative 2. Okay? Yes, there is a lot of work on these. Okay, example 2. See if I can get this lined up. Example 2, I have, let's see, I'm going to do 7x plus 2y equals 24, and 8x plus 2y equals 30. Now, remember I said you need to be looking for that coefficient of 1. Well, I have a 7, positive 2, I have an 8, and a positive 2. So none of these have a coefficient of 1. However, if you notice, this one, all of these terms have a common factor of 2. And one of the things with properties of equality is I can divide everything through by 2. So I now have 4x plus y equals 15. If I were to graph this black linear equation, and if I were to graph this pink one, they're going to be on the same line. They have the same slope, they're going to have the same y-intercept. So now what I'm focusing on is this equation and this newly written equation. So now I have a 7 and a 2, a 4, and then here's my 1. So I'm going to solve for this y. Subtract 4x on both sides. So I have y equals 15 minus 4x. You could have written it as negative 4x plus 15. It wouldn't have mattered. So I know that y equals all of this. Here's the key part, is that piece has to go into the other equation. So I have 7x plus 2 times my y, and my y is all of that. So I have 7x plus 30 minus 8x equals 24. And we're right back to simplifying and combining like terms. So 7x minus 8x gives me a negative 1x. Don't forget about my plus 30 equals 24. Solving for x, I'm going to subtract 30 on both sides. And have negative 1x equals negative 6. You cannot stop with a negative variable, so we're going to divide both sides by a negative 1. So x equals negative divided by negative is a positive 6. So right there I have half of my required ordered pair. So I need to put 6 into either this first x or in this second x. It doesn't matter. I'm going to go ahead and do it in the first one just because it's first, no particular reason. So 7 times my x of 6 plus 2y equals 24. 42 plus 2y equals 24. I'm going to subtract 42 on both sides to solve for y. And I have 2y equals 42 minus 24. Gives me a 3 and an 8 and a 1. Gives me a negative 18. Divide both sides by 2. and I get y to equal a negative 9. Remember to write it as an ordered pair. So I have the ordered pair of 6 and negative 9 as my answer. And again, I'm going to check it. So I'm going to do this kind of quickly in my head, if you will. So 7 times 6 is 42. Positive 2 times a negative 9 gives me negative 18 equals 24. And 42 minus 18 does give me 24. So that checks in the first one. I'll do the same thing to this one. 8 times my x of 6 gives me 48. 2 times my negative 9 gives me minus 18, or a negative 18. So I end up with 30 equals 30. So it checks in that one as well. So this is my solution. Now, I'm not going to complete this example, but kind of giving you a heads up of what you're looking for when you are trying to solve an equation by substitution. So negative 3x plus 7y equals negative 16, and negative 9x plus 5y equals 16. So again, we're going to be checking our coefficients. There's a negative 3, 7, and a negative 9, and a positive 5. There are no coefficients of 1 or a negative 1. 3 and 7 and 16 have no factors in common. 9, 5, and 16 have no factors in common, so I cannot divide out a 2 or a 3 or anything like that. So if I had a choice, this would not be one, not a good system, for substitution. Would not be a good system for substitution, and that is because no coefficients of 1 or negative 1. This would probably be fairly ugly graphing as well. So this would be a good candidate for the next method, which is going to be elimination, which we are not learning today. But just know that there are good times to use substitution and some not so good times to use substitution.